Okay. Good day, everyone. I hope you all can hear me. Can I get a thumbs up if I'm being heard clearly? Okay, good. Thank you. So, good day, everyone, and thank you for tuning into this webinar that is brought to you by the Asphalt Institute Foundation. My name is Dr. Amma Agbedor. I am the Senior Canadian Regional Engineer and Research Engineer for the Asphalt Institute, and I am honored to be your moderator for today. This webinar is being recorded, so please be aware of that. You are all muted as you come in, and there are a lot of you still signing in. So welcome everyone. You are all muted as you sign in, and if you have any questions throughout the webinar, you can ask them through the Q&A function of this Teams meeting. So as you can see by the title that I'm sharing, today's webinar is the binder properties and pavement cracking, validating durability and with the European field studies and aging models. That is a long title for our webinar, but you'll understand why when we get through the information. So the webinar is brought to you by the Asphalt Institute Foundation. As I mentioned, it is a public charity that meets the requirements of a not-for-profit organization. And AIF conducts strategic research and educational activities, as you can see here, that's on your slide there. And the educational activities and research are designed to advance and improve both the liquid asphalt industry and the welfare of the general public. You can scan that QR code and get more information about AIF on your own time if you're curious about all the work that AIF does. And if you're curious also about how AIF determines what strategic research is needed, actually, every few years, AIF hosts what's known as the STAR Symposium. And what the STAR Symposium is a strategic asphalt research symposium which brings together industry leaders to identify and kind of talk about what are the research and innovation needs of the industry to keep it robust for generations to come. So the first symposium was in 2017, and 100 industry leaders came together for this very purpose. And out of that symposium, AIF actually awarded research funding to research groups to study both the sustainability and the durability of asphalt binders. And one of those research groups was led by Nunez for the project that we're going to be talking about today, which was the Asphalt Durability Project. And the purpose of that project was to develop research methodologies to evaluate asphalt durability over a much longer time scale than what the current specification systems had in place. So the research team was led by Dr. Hilde Sunen at Nunez, and they completed much of that work in 2021, and they've been building on that work since then, which is what's led to today's webinar. So you can see the team listed there, but there are going to be two presentations. The first one is going to be from Dr. Hilde Sunen, and then the second one is going to be given by Dr. Hanyu Zhang. So during the presentations, please use the Q&A portion of the Teams meeting to ask your questions. And what we're going to do is after both presentations, we're going to have a Q&A period. During the Q&A period, the whole research team will be available to answer all of the questions, not just the presenters. So that's going to make for great discussion there as well. And we'll just gauge based on your engagement, how many questions we get and how encouraged you'll be to stay for as long as you can to get all the answers. But we'll get to that point, after we get through the presentations, I will now like to please hand it over to Dr. Hiltsunen and to start off our presentation that has drawn so many people because of just the sheer interest in the topic.
Thank you, Amma, for your nice introduction of the project. Wait, I did something wrong, I think. But yeah, I took the wrong one. Sorry. Can you see my screen? Yes. Okay, thank you, Amma, once more for your nice introduction, and also a warm welcome to everybody joining us today. It's amazing to see so many people interested in this topic. So I will try to summarize the main outcomes of our project in 20 minutes. I hope this will work. First page down. Okay, so as Amma already said, we have two parts, and I will start now with the experimental part. The objectives, Amma also already told this a little bit. So we are looking for binder properties related to asphalt cracking. And we would like to know what property on the bitumen is it that we should test to determine the risk for aging-induced fracture, and can we set limiting levels on this? Another question is to see how the aging is penetrating through the asphalt surface layer. And another part that we wanted to look at is to see if laboratory aging, and in this case we focused on the pressure aging vessel, if this test is simulating the aging that we observe in the field. And we focused, in fact, on two binder parameters, so the Glover-Rowe, which is, in fact, derived from ductility on a binder, and also on delta TC, which has also been proposed, so which is at low temperatures, the difference between the limiting temperatures from the PBR. Regarding the methodology, so of course we first needed to select pavement sites, and we wanted to have pavements that have aging, so they needed to be at least 8 years old. And we also wanted to have info on the road performance or the road condition. These two conditions are not easy, so it was not to select pavement, but just to find pavements that were there, where we could get cores from. And once we were able to get cores, we tried to take a large number of cores from the same spot. And all the cores were taken from between the wheel paths because we were interested in the aging. So once we had enough cores, density measurements were conducted, nuclear density, which has the advantage that you get a density number every millimeter. And after that, we sliced the cores. And in this case, you can see we used very thin slices. First, we put markings on 0.1 centimeter, then on 1 centimeter, and then every centimeter. And you see during the slicing, a lot of material get lost. So you end up with very thin slices, and we needed at least 5 cores to get enough material after the binder recovery so that we could still do some tests. And the main tests that we did was rheology and infrared spectroscopy. We also did some other tests, but those I will not discuss today. The whole procedure that we followed has already been published, and at the end we will give some references where you can find these papers. Okay, then regarding the field sites that we selected, in a project before this one, we had already looked at a number of sites all over Europe, even one site in Morocco. And during what we call AIF project, we added 5 new sites to the project, as you can see here. I will not go into details to all of these sites, but a few of them. For example, we had a site in France, which was from the highway between Paris to Lyon. It's a very trafficked road. And there were two sections, one from 2004 and one from 2010, which you see here, the pictures. The one from 2004 was, in fact, end of life. And we also got the performance evaluation from the French road authorities, but they, in fact, end up with 3 levels, 3 severities, and the older one was severity 3, and the pavement from 2010 was severity 2 in that system. Then we had a pavement in Belgium. This was a local road constructed in 2009. And in fact, this was a test site for warm mix. We had a warm mix section based on zeolites, so replacing part of the filler with a zeolite. Then we had a hot mix reference section, and we had again a warm mix section based on a wax modified binder. Unfortunately, for this last section, we could not recover the wax modified binder. So this was not included. But the zeolite section we could split into 2 because the first part was really suffering from raveling. You already see it has been repatched. So we took course in between these maintenance areas. And then we had a second part where we could also take course, which had mainly raveling, as you can see here. So the performance on this test track was on one way done by a visual inspection from the Belgian road authorities, but we also applied an automated scan here, and here you see the mean texture depth, which was in the road center. So there was quite some raveling, which was not due to traffic. So, and then I have a last section to show you, which was from Czech Republic. It was again a local road, a binder from 2014. And in this case, we got an evaluation of the performance from a consultant, which divided it in 5 levels, as you can see here, depending on the amount of damages that they observed. And this road got a severity 2. So you see that even the road authorities apply different systems over Europe, and even consultants use visual classifications. Now I come to the first part to discuss some of the results. So regarding the aging gradients, how the aging penetrates through the pavement or to the surface layer. I have here some slides from the Belgian side where we had a reference and a zeolite. And you see the Glover-Rowe versus pavement depth. So in this case, the air voids are 2.8, and this one has a bit more air voids. But you can see, even for the very dense asphalt, you still have quite a gradient. And on average, it is aged less compared to one with higher air voids, but the gradient is even larger. Now I showed you log Glover-Rowe, but I can as well show you the delta TC level. So you see it shows the same shape as the Glover-Rowe parameter. And in this case, and we observed that very often, we saw like a C shape in the properties versus pavement depth. And if we then looked at the nuclear density, even there we saw a C shape. So probably this is related to each other. If we then go to open mixes, so the two from the French side, you see air voids 9%. Now the pavement or the surface layer is aged all over. And this case 8.4, it still has a very minor gradient, but very little. So for the open mixes, in fact, the slicing would not be needed because the layer is completely aged. Then I come to the next topic, which was field aging versus long-term laboratory aging. This has already been presented at one of the STAR symposia, and it has also been published at the ENE conference, so you can find more information there. But I will just go through one of the highlights. So we looked in this case at stiffness data at different temperature regions for one section. So for this Belgian section, we still had the original binder. And this is again the one with zeolite with the 7% voids. And you see the comparison at 50 degrees here. So the original, this is the standard aged, so RTFOT and 1 times above. And then we did a continuous aging up to 4 times pressure aging vessel. And you can see these 3 are the field aged slices, that the 4 times PAF comes close to what you see in field aging at 50 degrees. But if we then go to lower temperatures, for example, here, frequency sweeps at 10 degrees, the same sample, the same binders, you now see that the lab-aged samples are all below the field-aged samples. So lab aging is not, in this case, not sufficient to simulate the stiffness that you see in the field. And if you go to very low temperatures in the range of the bending beam, yeah, in this case, this was measured with the 4 millimeter DSR, but all the samples were measured in the same way. And you see the lab aging is in this region and the field aging is here. So there is an even larger difference now in the stiffness levels that you observe at very low temperatures compared to lab aging. If you would have to age this one to the same stiffness as the top slice, you would need many lab PAF aging cycles. So I come now to the conclusions of this section. So as mentioned, rheological properties, the trends are similar, but in field aging, stiffness increase is larger, especially at low and intermediate service temperatures, and these are just the temperatures where we get pavement cracking. We also did stress strain sweeps, which I do not show you in this presentation, but we saw brittle fracture after field aging and ductile behavior after laboratory aging. Regarding the chemical properties, we also noted some differences. There are much more sulfoxides in field-aged samples compared to the sulfoxides you see after the pressure aging vessel. And regarding the rankings, we had 2 binders for which we still had the original samples, but these 2 binders were from the same origin. So unfortunately, we cannot say whether the pressure aging vessel can still discriminate the binders regarding the ranking that they would have in the field. So no conclusion on this last item. And now I come to the last part of the presentation. So what did we do with the damage, or how do we compare the damage versus the binder parameters? So we ended up with an Excel sheet having all our pavement sections, having the data. And regarding the damage, we were inspired by this consultant, and we also decided to use 5 qualitative levels. So we had a 0 with no damage, 1 was then very little and local, 2 is more but still local. Here you have to change from local to connected levels, and 4 was end of life. And in this evaluation, we considered all type of cracks, except if we knew that there were reflective or cracks, or if there was a base layer or support issue. So because of that, 1 section was removed. And for this Belgian section, we also included raveling as a damage parameter. So in this slide, I now look at the AIF sites we investigated, only the top slices, data from the top slices, and we look at the Glover-Rowe parameter. So in total, we have 11 sections, and they are plotted in a black diagram. So in our study, we used the Glover-Rowe determined at 15 degrees and at the very low frequency level. And you can see the 0 is the lowest and the 2 with a number 4. So these numbers are damage levels. The 2 with a number 4 are on a high side. You could argue that this 3 could be an exception and this 1 could be an exception, and also the 2. So I looked a bit further which ones these are, and you can see it's highway and a highway, and this is a local road. So probably the traffic, as we expect, will play a role as well. And in this graph, you see the damage versus the logarithmic of the Glover-Rowe. And the correlation is 0.59, which means, in fact, that the variation in the damage is for 59% determined by the logarithmic of the Glover-Rowe, which is a lot if you consider all the variations between the sections. So then we did the same thing, but for delta TC. And this is now plotted in a diagram showing the limiting M temperature versus the limiting S temperature. And here you see the number 4, for example, once it is above the critical line and once it is below, there is a one above the critical line and some are below. Here is a lot above. So if you now plot damage versus delta TC, you see that there is no correlation that we could find. The next graph here is now all the sections, the 24 sections. So you see again, there is quite a correlation. There is one exception here, which is if you do it statistically, it is seen as an outlier, but in fact, this is an airport pavement and it is a highly modified binder. So probably that is the reason why it is an outlier. So if you look in the graph damage versus logarithmic Glover-Rowe, it is the point here, which is in fact the point which makes the correlation a bit worse. But still we are at about 50%, which is a lot if you consider all the variations here. And we also see that the proposed limiting levels, so the warning of 180 kilopascal for the Glover-Rowe ends up close to a level 1 in the damage, and the 600 is the change from 2 to 3, which is in fact, yeah, where you have already some damage and move to the connected levels. We did the same thing for delta TC with all the sections now, and again, there is no correlation that one could see here. And this is the last slide on this. We also did a graph only using the highways, so just to separate a bit the traffic. And now you see it's an even better correlation. One reason is, of course, that this airport pavement, which was outlier, is now gone. So that's also playing a role. What else did we do? Since we had so many sections, we were able to do a significance analysis. So assuming a null hypothesis that there is no relation, and then you check what is the probability of having this null hypothesis. And the lower this probability is, the more significant your correlation is. So in this case, it's very low, so we can reject the null hypothesis and say that there is a real effect here. So almost 50% of the variance in damage is explained by the Glover-Rowe. We did the same thing for some more parameters, as you can see here. So using the limiting M temperature, the limiting stiffness temperature, the crossover frequency and the crossover temperature, and you see that they all have about a very similar coefficient of determination, and they are significant. On the other hand, delta TC or the log crossover stiffness, they did not show a correlation. And finally, from FTIR, if we took the sum of carbonyls and sulfoxides, in fact, there we found the best correlation and also very significant. So as a conclusion, so our qualitative damage levels indicate a significant trend with the Glover-Rowe, while no relation was seen with delta TC, and the proposed cracking limits, they fit the observations. Slicing would not be needed for open mixes, but for dense mixes, the slicing allows you to capture the gradient, but your value will also depend on your slice thickness. So that is leave that as an open question whether you really need to use this 0.5 centimeter, because that's very thin. Then some other observations. So we still use the qualitative level, damage level, because there was no unified method used by the road authorities. And even if you have the damage, it's not always sure what are the reasons or where it comes from. Very often you can determine it from the shape or from the crack shape, but not always. We also noted large differences in compactions for the same site. So therefore, we focused a little bit more on the damage around the coring site. And we also excluded places having high shear forces like curves, traffic lights, crossings. So we looked more at the straight parts in the sections. And with this, we've come to the end of my presentation. So now I will hand over to Hanyu.
Thank you. Here's trying to share my screen. Yeah. Can you see my screen now? All right. Thank you. Thank you, Hild. Hello, everyone. Thank you so much for joining us for this AIF webinar. I'm Han Yu Zhang. I was very lucky to be involved in this project when I was doing my PhD at University of Nottingham with Gordon and Yuqing. I would like to thank AIF for the support and also thank Ninus and Colas for the great support and collaborations over the past few years. So let's start the modeling part of our project. Yeah, I think as mentioned in Hild's part, we've already had a lot of observations on the field agent, and we realized that agent has a substantial effect on the asphalt materials, the binder properties, and also the pavement performance. So what if we can have an agent model that can duplicate the field observations? That would be great, a powerful tool for us to test different binders, different materials. So one of the objectives here is to develop a pavement agent model. And this model needs to obtain the different pavement agent profiles based on the on-site specific environment. And it can also distinguish the binders with different agent sensitivity, and it also needs to capture the effects of air voids on pavement agent, because we all know agent is highly related to the air voids. And then once we have the agent model, we validate the agent model, we need to develop the pavement performance model, which can consider agent. So the performance model needs to obtain the pavement remaining life considering agent. It also needs to distinguish the pavement performance that was built with different binders. I would like to emphasize here our experimental part and the modeling part. They are not separate works because all the model developments and validations are based on the experiment part. So for the modeling framework, I believe most of you are very familiar with agent. So we need to understand the mechanisms for the asphalt agent in the pavement. It is a very typical diffusion and reaction process. So which means that the pavement temperature must suffice to activate this oxidation process. That refers to the first physical process here, heat transfer along the pavement depth. Now we have the temperature. We also need sufficient amount of oxygen for the oxidation. That refers to the second physical process here, that is oxygen diffusion. Once the temperature and oxygen are ready, so the oxidative reaction can happen. That is the third physical process here. So to sum up, pavement agent is a multi-physics phenomenon that is highly associated with temperature and the oxygen amount. Then after we understand the aging mechanisms, we need to formulate a series of equations so that we can model payment agent using numerical methods. The credit here goes to Professor Charles Glover and his team at Texas A&M University for developing those coupling equations. So for our project, we developed our agent model based on their work. I would like to know that in our project, we use carbonyl. We select carbonyl index as the agent parameters because we think it's still the most appropriate indicator for quantify agent in terms of the current mainstream binders. Now we are able to model agent, then we need to figure out a way how to couple agent with our mechanical models with the mechanical analysis. So for our project, I developed this time, temperature, and agent shift model based on the frame value theory. And this theory tells us that all the external factors like temperature, agent, solvent, concentration, they're all changing the molecular volume system and the molecular motions, and it changes the macroscopic material properties like the viscosities and modulus. So by using this time, temperature, and agent shift model, we can simultaneously consider the effects of temperature and the agent on Oxford materials modulus change when we are doing the mechanical analysis, the mechanical modeling. Now we have the pavement agent model, and we also have a method to couple agent with mechanical analysis, but it's still not enough because we want to know the pavement damaging behaviors under the coupling effects of agent and vehicle loads. So I developed this viscoelastic continual damage model for asphalt concrete based on Professor Shapery's through-the-stream concept. So by using this damage model, we can know the indications of pavement remaining fatigue life based on the current pavement aging conditions and the stress state. So this slide shows the workflow of those different models. So first we conducted the pavement agent modeling, and we output the functions of temperature and the carbonyl index. It's related to the time. It's an evolution function. Then we input those functions into the shift factor. Then we input this time, temperature, and agent shift factor into the viscoelastic continual damage model. So we can obtain the pavement damage conditions when considering the agent effects. So I'm going to introduce the model validations. Actually, we spend a lot of time developing the model and also a lot of time validating the models because the model predictions or the model applications wouldn't be reliable if we don't have enough validations. Here I selected 4 different row sections in our project. There are enough testing results and measurements for validating different parts of our models. So this slide shows the comparison of the modeled and measured temperatures in both summertime and wintertime at 2 centimeters below the road surface of one row section. So we see here the model can capture the daily temperature variations and the seasonal temperature changes. So I would say the model is valid in terms of predicting pavement temperatures. The next part of validation is about the carbonyl index prediction. So this slide shows the comparison of modeled and measured carbonyl index, which we use for quantifying agent. So first, we say that this model can describe the different agent gradients based on the site-specific environment conditions. If we have a look at the right figure, it's the agent gradients, the modeled agent gradients and measured agent gradients using carbonyl index for different binders used in the same row section. What we see here, the model can distinguish the agent evolutions of binders with different aging sensitivities. Then if we look at the left figure, we use the same binder, but the cores, the different part when we drill the cores have different air voids. And what we see here for the left figure, the model can identify the effects of air voids on aging evolutions and aging gradients. So we are not going to perfectly match the measurements because it's almost impossible. But the model is useful if it can have the three features as shown in this slide. This slide shows another two comparisons for another two row sections for the carbonyl predictions. And so we have validated the agent models in the previous slides. In this section, sorry, in this slide, I'm going to show the validations in terms of the material constitutive model, that is the viscoelastic continuous damage model. This figure shows the comparison of the modeled and measured strain response in a cyclic indirect tensile fatigue tests for the field cores. What we see here, the model can capture the strain evolutions on the fatigue load and the transition load cycles before the final failures. So the model is valid in terms of describing the asphalt fatigue damage behaviors. The final part of model validations is for the payment response model. Here I use the FWD measurements and their back calculated strain as the benchmark. So we see that the model can capture the payment response under the FWD load, and it also captures the evolutions, the response evolutions with the agent. So as we expected, and also showing in the right figure, we see with agent, the strain at the bottom of the asphalt layer decreases because we have a stiffer asphalt layer after agent. So after completing all the different parts of model validations, now we are confident to do some predictions, to have some applications of our models. The first model application is the fatigue life prediction considering agent. So this figure shows the Mises stress distributions at different agent time. So what we can see here with agent, the high stress regions moves from the bottom of asphalt layer to the road surface. So it potentially changes the cracking mode from bottom up to top down and maybe further contribute to raveling. This finding is also consistent with one of the NCHRP project regarding top-down cracking that was led by Texas A&M University. We in the previous slide, we already see that the aging effects when we use a stress indicator. This figure shows the pavement damage conditions after 100,000 load cycles at different aging time. So the major finding here is that in our case, for this row section, 16 years aging would introduce more than 50% extra damage on the road surface, both within the loading area and at the edge of the loading area. So I think it potentially contributes to the longitudinal cracking along the vehicle, along the wheel path. Now we understand that aging has a substantial effect on pavement performance, but we still need a quantitative indicator to show the aging effects. So this figure, the figure in the left, shows the remaining fatigue life predictions at different aging years. The right figure shows the comparison of the minimum remaining fatigue life predictions with and without aging considerations. What we see here in our case, in this case, 16 years aging would shorten the pavement remaining fatigue life up to 1.6 years when we only consider the effects of aging on pavement modulus change and the modulus gradient. What we didn't consider here is that we didn't consider the material degradation in terms of damage tolerance with agent. So imagine if we include this part of effects in our modeling, I believe we'll have much more difference, more than 1.6 years, I believe. Now, the second part of model application is the performance comparison of roads built with different binders. That's mainly for the material selections. This figure shows a comparison of pavement remaining fatigue life predictions of 4 trial sections in the same road sections in Sweden. We use different binders, but they are used in the same location. So what we see here, the two polymer modifying binder sections, they demonstrate outstanding performance when we compare to the reference and EVA sections. In this slide, so the left figure shows the comparison of the pavement remaining fatigue life predictions of the 4 trial sections with and without aging considerations. And the right figure is a comparison of the laboratory tested fatigue performance of the field course. So what we see here, the modeling performance ranking is consistent with the laboratory test results as well as our field inspections, as shown in field in the experimental part. So which means if we use the work, we can have some prior understandings. We can have some indications for the pavement performance. If we want to use, for example, a new binder or a polymer modifying binder or other materials, before doing the construction, we can do the modeling, so we can have much more information before we make the decision. So yeah, here's a summary for the modeling part. First, aging gradient, like we observed in the field, aging gradient is as evident as temperature gradient, and we should consider it in pavement mechanical analysis and performance predictions. Second point is carbonyl index is a fundamental parameter to quantify aging evolution and aging gradients in the pavement structure. So it can replace the empirical modulus-based aging characterizations. I think maybe more than 20 years ago, when we developed the global aging system, developed by Professor Wisak, we use viscosity. Then in one of the NC HRP projects led by NC State University, we use modulus. Now in our project, we decided to use carbonyl index because it's a fundamental property of the mainstream binders. Then our model has been validated at different scales in terms of material scale and structural scale. And the model has been validated using different measurements. We use the temperature, we use the carbonyl, we use the FWD response to validate the model before we do any predictions and applications. So we see here, according to our findings, field aging will change the positions of the high stress region or the most dangerous position from the bottom to the road surface. So it potentially contribute to the top-down cracking. So in our case, 16 years field aging would introduce more than 15% extra damage on the road surface, mainly localized at the edge of the loading area. So it potentially leads to longitudinal cracking. In our case study, field aging would shorten the pavement remaining fatigue life up to 1.6 years when we only consider the effects of aging on modulus change and the modulus gradient. So if we consider more, we consider the material degradation in terms of damage tolerance, we'll have much more difference for the aging effects. So our model have two major applications. The first one is to predict the pavement performance, consider aging effects. I think this is mainly for the design, for the analysis. The second application is to compare the performance of roads built with different binders. Like I mentioned in the previous slides, if we have different binders, we know that they had different performance according to the lab testing results, but we are not sure how they will behave in the field. So we can do the modeling. We can have some prior understandings if we really want to use the materials. The next point is that our model can consider. I think our model can consider the effects of maintenance and rehab when we try to extend the remaining service life of the existing payments. So we can start modeling based on the current conditions, based on the current material properties. Then once we do the resurfacing or we do the treatment, we can either fabricate the samples in the lab or we take the course, then we test them, we get the material properties and we input them in the model so we can model the performance enhancement because of maintenance, because of other treatments. Finally, the model can be compiled into a program or a module of the Ashtaware Pavement ME design. So it would be very user-friendly for different practitioners. Yeah. So here, this is a list of our publications produced from this project. I think many details we can't present here today. I think you can find them in these publications. Yeah, I think it's pretty much of my presentation today. Thank you. And please feel free to ask if you have any questions. Thank you.
Thank you so much, Dr. Hill Sunan and Dr. Han Yu Zhang, for both very engaging presentations. We do have some questions that came in. Just a reminder to everyone who is logged in. If you have any questions on any of the information that was presented, you can type them in the Q&A and we're going to get through them now. So I'd like the rest of the research team to also turn on their cameras, and any of these questions will be open to all of you to give your input. So the first one that I see here is from Chatbot, and the question is, what are some suggested modifications to lab aging protocols from the research team based on the data that you're showing that there's some discrepancy between the field and the lab? And the follow-up to that too is, for dense graded mixtures, should the aging be done separately for surface mixes as opposed to the base mixes? I'll leave that open to the team.
Okay, maybe I will start with the first part of the questions. Yeah, finding a new aging method was in fact out of scope of the project, but in fact, maybe it's more my personal view. I think the temperature should be as low as possible, but there is a rule of thumb. If you decrease the temperature by 10 degrees, you have to double the time. So of course you can't go too low in temperature because it will take you a lot of time. But at least from the project, we had indications that at higher temperatures, the sulfoxides, they disintegrate, and if they disintegrate, probably they increase the aromaticity of the system. And we noted that larger aromats are formed at higher temperatures, and these increase the stiffness at higher temperatures, but not at lower temperatures, and that's why we saw the discrepancy. That maybe it's more my personal view, but and we are still at the moment looking at other aging tests. For example, we have sent a sample to Vienna where they did the Viennese binder aging test, where they use radical species to accelerate the aging. And now we also send a sample to Delft University in the Netherlands, and they use peroxides to accelerate the aging. So maybe that are ways where you can avoid having a high temperature and still get to a reasonable time. The second part of the question, I'm not sure if we should age dense mixes So surface layers, I think we could age more compared to base layers, and for the dense graded, yeah, on average they age less, but at the surface they still have a lot of aging. So I think we need more data there to see if the thin, very aged, very top slice, even on dense mixes, how important that is for the damage. I don't know if somebody wants to comment. Anu or anyone else?
No, they're very good questions. I don't think there's a simple answer to either of those questions in terms of we know that lab protocols don't always replicate what happens in the field, and there's been various studies, NCHRP studies, and obviously other PhD studies around the world that have looked at that. The dense question in terms of surfacing and base materials, again, most of our aging, as you would probably appreciate, is going to be linked to the surfacing materials because of the fact that they're on the surface. They're exposed, obviously, to higher temperatures in general, obviously environmental factors or conditions as well, UV radiation, etc. So that tends to be where we concentrate most of our aging in terms of trying to understand, what's going to happen in terms of field performance.
I think that'll be a good lead into this one that's got one vote on it. Very interesting, the graph. So what are your thoughts on possible reasons behind that C-shape property change through the pavement depth that you were showing for some of your different properties?
Anu, do you want to answer or?
Well, yeah, I think yeah, because normally we think the aging gradient would be like a R shape. It wouldn't be like where you have both higher values and both the surface and the bottom. Yeah, but that's based on our findings. When we take the course, we didn't know it would have a C shape, but when we sliced them and we tested, it did has this C shape. So I think one of the assumption that we make when we are doing our modeling is that you gotta have more like oxygen accessibility if you have like uh, uh,
We don't hear you.
base. Yeah, but at that time I think we don't know the base type. Yeah.
I think we got cut off with some of your response there, but anybody else want to comment on that interesting C-shape property change through the pavement depth?
I think Hanyu is right. The C shape is highly related to the air volts distribution, since we have the C shape distribution of the air volts along the pavement depths. Another factor is the base layer. So if the base is like a unbound aggregate base, we have more voids, so more available of the oxygen from the bottom. So that will give you a higher oxidation at the bottom of the asphalt layer. But however, if we use the treated base, which is more dense, like a cement treated base, which we use a lot in China, in that case, we may not have the C shape of the aging. In that case, you will typically see a decrease in aging along the pavement depths. So I think the air volts distribution and the base type are the two main factors determining the shape of the aging along the pavement depths.
Yeah, very interesting and logical perspective, linking air voids to distress levels, which have been documented, and now you're seeing it in air void distribution through the pavement depth, and also the link to the air voids in the base type as the reason for the coming. Yeah, that makes a lot of sense when you think about it that way. So thanks for clarifying that. There's another, there are a lot of questions that just came in. Okay. So let's take a chemical one. Did you look at the change in chemical components as such as the effect of asphaltene or resin fractions and how they relate?
Yeah, we did a few tests on this Belgian section, but only up to 2 times pressure aging vessel. And if we compare the Sara fractions at the same aromats, so we had a field section that had exactly the same amount of aromats compared to this 2 times pressure aging vessel sample. We have for the field aging less asphaltenes, but more resins. And that would also fit with having smaller aromats that react, because they are still not so large that they become asphaltenes. While in the pressure aging vessel, they are large enough to fall after reaction into the asphaltene fraction. That was a hypothesis. We were unable to prove it, but it would have fit with these observations.
So this is
answers the question.
Yeah, so this is also kind of explaining why you see the differences between the two different aging types. Yeah, thank you for that. Okay, let's take another question. So a few questions about the publications. We're going to have access for the ones that are publicly available. We'll also make them available on the AIF website. So within the next within the next week, you can check and we'll have them available there. And any additional work that is being presented, you can find them through sites that publish research work. So maybe Science Direct or ResearchGate or places like that. They'll be available there. There's a question here regarding the modeling. Can the model also predict the performance of different asphalt mixes based on air voids for given asphalt binder?
Yeah, I think I saw the question. Yeah, I would like to clarify that we are not, the model is not like predict the performance based on the air voids, but actually once we have the material, if it's the same binder, but we have different volumetric designs, so we have different volumetric parameters, so they will behave differently. But what we need to do just to test them, some fundamental tests and get the fundamental material properties and input them in the model. So we can see then we can see the difference. Yeah.
One point I want to see here, fundamentally embedded in the model, we relate the air voids with the oxygen diffusion coefficient. So that means if you have different air voids, your oxygen will diffuse in a different rate. And that will change with pavement depth as well. So that means when we have a C shape of air voids along pavement depths, we will have a C shape of oxygen diffusion coefficient in the model. That will quantify how the air voids affect the oxygen diffusion, in the end, affect the aging profile in the pavement. So basically, yes, we can take into account the aging, the air voids in the mixture.
Okay, so hopefully that answers that question. There was a comment and question here around field aging will exhibit UV aging, which will contribute to the carbonyl index. How do you account for UV aging in the lab setting?
Well, I think, yeah, sorry. Yeah, definitely. Especially in some part of the areas, UV could be a like dominating factor instead of only have oxidative agent. But for our case, the European cases, I don't think UV agent could be the major cause for the field aging. So that's why we still focus on the oxidative agents. And I think there's one standard, but it's not for, I think there's one ASTM standard. I can't remember the name, but there's one ASTM standard that specify the testing protocols if you want to use like a environment chamber that have a like a UV light, something like that. It has a testing protocol in ASTM. I think you can find one for bitumen.
Okay. All right. So there's a question about whether you can give some reasons, some possible reasons for the differences that you found where there was good relation drawn for the Glover-Rowe, but not good relation drawn for the delta TC. Maybe you can talk us through some of the reasons why that was.
Yeah, maybe I can start to cite Jeff Rowe. So the Glover-Rowe parameter is in fact, it's a point measurement. It's something that's dependent on temperature and frequency, while the delta TC is a parameter relating to the shape of the master curve. He used to compare it with the Glover-Rowe is something comparable with a penetration, and the delta TC is then comparable to a penetration index. It's more telling you how the behavior is, the susceptibility versus temperature or frequency is changing. And we see in this research, the results show that the parameters related to point measurements, they correspond to the damage. And the ones relating to the shape parameters, there we don't see a relation to the damage. It's similar if you look at PEng and PEng index. The PEng index will not relate to the damage directly. But yeah, it's still strange because if you look at the same binder and you look versus aging, your delta TC will change with aging and the Glover-Rowe parameter as well, and they will correlate if you have the same binder. But if you start to add different binders, your correlation is lost. And yeah, we see that with field, it correlates only to the Glover-Rowe and other point measurements. Don't know if someone wants to add something.
No, I think it's a really good explanation. The key thing to remember between a point and a shape parameter, point parameter for this particular example with the Glover-Rowe is measuring some form of stiffness. And if everything has roughly the same stiffness, then you probably want to look at the shape parameter as a secondary type parameter to help you understand the influence of different materials to damage. But I think for most of our cases, it is going to be based around a stiffening effect. Obviously, a stiffening effect would tend to be more will have a high ability to pull stress into it in terms of it making it more susceptible to cracking. And that's why you're probably seeing with that point parameter, with that Glover-Rowe, a much better correlation or relationship with the damage caused by aging and leading to cracking.
Great, thanks to you both for those responses. Here's one that's maybe linking both presentations. It says that the first presentations showed the sum of the carbonyl and the sulfoxide in both as the best predictor. But I guess in the modeling, you only use the carbonyl. So I guess the question is, do you think the modeling would be improved if you used both versus just the one?
Well, I think one of the reasons we select carbonyl instead of the sum of both carbonyl and the sulfoxide is because we saw different evolutions when we measure the. So we have the laboratory aged binders, and we also have the recovered binder from the field course. We see the different evolutions of the sulfoxide. So which means if the evolution or if the change of sulfoxide is different in the lab and in the field, we can't. It's really difficult to get the aging kinetics parameters because we need to use the laboratory protocols to age them in the laboratory, and we need to test them and to get the agent kinetics parameters. So because that, I think that's one of the major reasons we only selected carbonyl. Yes, of course we can select. If I know some of the papers saying that the sum of carbonyl and sulfur oxide, they have better correlations to G star or to E star or to other rheological indicators. But what we want in the model is just like fundamental properties, because we found carbonyl is keep increasing. It just keep increasing, so it can have a better indications for the aging quantifications.
Yeah, and we also found a rather good model correlation between damage and carbonyls. It was a little bit less good than the sum of the two. That's why I did not show the carbonyls separate. But they also gave a correlation. And when we started the modeling, of course, we didn't know that the sum would give the best correlation that we saw now afterwards.
Okay, just so that everyone is aware, we have gone 6 minutes over our time. I've spoken with the presenters ahead of time, and they are prepared to stay for 15 past the hour to answer a couple of more questions. And then based on how many questions are left, we will decide how to respond to everyone else's questions that didn't get answered. So if you still have a question that you would like to ask, just so that you know, we are going to stay for, I guess, another like 11 minutes. Okay, so I'm gonna go through here. This is a long one that's just come in. All of the selected pavement sections are 8 years or older than 8 years, as per Charles Glover. There could be a fast rate of oxidation in the first year of aging. How could you validate your model for it? So I guess this is for Han Yu. Also, climate plays a role in the field aging. How did you incorporate this in your model? Also, FTIR carbonyl index can be changed for unmodified and modified binder. How do you calibrate the model? So this is quite a lot of questions in the one, so you can take your time with it.
Yeah, thank you for the questions. I think for the first part, you mentioned that, based on Professor Glover's work, they proposed the two stages aging kinetics equation, the fast rate and the constant rate. But I don't think what we do here is that we use a thin film of an agent for different aging durations and different temperatures, and ideally we need to do it at different oxygen pressure. So that would give us a curve, the carbonyl index versus your aging time, and you have multiple curves that's on the different temperatures. So through that curves, you can identify the two stages. The first part in Charles Glover's report, they said the one before 24 hours, if I'm right, that's for the fast rate period, and the remaining part is for the constant rate. So we use the two segments of the curves to derive the different part of the coefficients for the aging kinetics model. And the second question is about climate. How did I incorporate? Yeah, the climate. So I didn't. Yeah, the climate, because we have the because aging is associated with temperature, and we have a temperature prediction part in the model. So if you want to predict temperature, you gotta include climate that is associated with temperature. For example, the ambient temperature, your wind, and the solar radiation. So that all of the climate factors that we included as the surface boundary conditions for the model. The last one is about FTR measurements may not be changed for how do you calibrate? I'm not sure, but are you asking how we calibrate the model if the carbonyl index is not changing. It,
Oh, there it is. Okay, yeah, I lost the question. So the last part was how you calibrate the model to account for unmodified or modified binders.
okay, yeah. I think for the mainstream binders, unmodified and usually we use polymer modified binders. What we see here, carbonyl is still a good indicator for quantified aging. So it doesn't matter if you. I think it also relates to if you can fully recover your binder, your polymer, or when you do the recovery, because that affects the measurements when we do the FTR. But from our project, I think carbonyl is still a good indicator for both polymer modified binder and unmodified binder. So that's why we think it in the model we can use it for different binders.
May I put two more points here? Actually, I remember we have the original binder for the section. So that means we can test the original binder which were used in those sections to determine the faster rate aging and the constant rate aging properties. In terms, we basically use the activation energy, which is the key parameter to determine the evolution rate of those binders. So we can determine the activation energies for the faster rate part and the constant rate agent. So that's how we take into account of the initial part. Although we have only the field section over 80 years, we can still predict from the model for the agent in the first several years. Actually, the output of the aging is an hourly based output. So it has a very high resolution of the output. I think that's something that I want to put for this. Yeah.
Great, thank you for your input. Okay, so I guess one more question to the group, because we're talking about aging, and with asphalt binders, aging is inevitable. So maybe some recommendations from the panel on how to address it through material development, structural design, construction, maintenance, all of those areas. How can we work on not making this a big issue, since aging is inevitable? Any recommendations from the panel?
That's a very good question. We could try to find anti-aging additives, but they may be expensive or not very efficient. We always used to say to use very dense mixes, then you avoid aging, at least in the depth. But yeah, now we saw that on the surface it's also even more aged. So in my opinion, a regular maintenance would help. If you, as soon as your pavement has aged a lot, you could use a kind of rejuvenator to reinstall the original binder properties, and in that way you could extend the lifetime for a long time. But please, if someone else has another idea or suggestion.
Yeah, I think I can add one point is that because we see this aging, the mechanisms and our testing results, our modeling tells us air voids could play a vital role in aging. So when we do the construction, if you are like a dense mix, just compaction is very important. So for like a constraint agent within the first top one, within the top 1 centimeter. So that's better for our regular maintenance. But if you don't have like a sufficient compaction, you will probably have let the oxygen easily go through your pavement depth. You have more aging for your lower layers. I think that's one suggestion.
What is important also maybe is that it gives us a lot of information regarding the real aging happening on roads in any kinds of wearing courses. And in that case, we see that for dense mixture, aging is very limited to the very top layer. So we have better understanding of how it evolves, and maybe it will help us to predict behavior and to have a better maintenance organization, starting it maybe sooner for some specific wearing courses. But another point is that we cannot use open mixes for all the surfaces. For some cases, we will need some open mixture for drainability and other specific characteristics. That means that we will have a better understanding of the aging, and we also need to improve the way we do the maintenance, taking into account in a better way the aging of the binder. But it's just beginning of we just began to get a lot of information regarding aging on binders from job sites. Before we are usually characterizing binder for the mix design, but we just look at the initial characteristics of the binder and how it evolves with the aging, but we do not have a real good experience of how it evolves on site. And this will help us to understand how to manage that in the future.
And a quick one, did the mixed slices contain any recycled binder, i.e. reclaimed asphalt pavement or shingles?
So some of the mixes, yes, had some wrap in it. At least one in France in the beginning.
Yeah, but it was less than 20%, I think.
Well, at that time it was not so high.
And shingles, there were no shingles.
Okay. All right. I believe, well, actually, no, there is one more. Is Gordon still online? Someone wants referring back to when we were talking about the Glover-Rowe parameter and delta TC, just more explanation as to how the Glover-Rowe parameter is better related to cracking than delta TC. Gordon online?
Gordon, are you still there? Maybe he left. Yeah.
I think if I can add a comment.
Oh yeah, absolutely.
Because so I think one of the reasons that Glover-Rowe performs better than Delta TC, because if you look at Glover-Rowe, they actually developed this based on the they call it DSR function. So when they developed the DSR function, they started from the constitutive model. They use a fluid Maxwell model to formulate this DSR function. Then they found DSR function has a very good relationship with binder ductility. So they decided to just simply use because there are some relationships between your the parameters in the Maxwell model and the G star and the phase angle. So they just simply replace those original DSR function with G star and phase angle. So that's the final formula. We call it Glover-Rowe. I think that could be a possible reasons because it started from the constitutive models. That's also one of the Professor Charles Glover's work, and they have some report on that.
Okay, thank you. Oh, we lost you. Thank you for your great explanations. We've gone over even what I had intended, so I want to respect your time that you've allowed for the panelists to go over. If there are any additional questions, I'm going to, I think everyone who registered has access to my email address or a direct link back to Jacqueline, who sent you the invite. Any additional questions, you can email them to us and we'll figure out if, based on the questions that we get, whether we can respond to them either through a posting on our website or if we need to do a follow-up discussion. But really great engagement from everybody. On behalf of the Asphalt Institute Foundation, I would like to thank all of the presenters and the panelists for such a great webinar. And with that, I would like to wish everybody a good rest of your day. Take care.
Okay.
Thank
Thank
you.
you.
Thank you, Emma.
Bye.
Thank you. Bye.
Bye.
Thank you. Bye.
Bye, everyone.